Welcome to a lesson with Dr. Powell. Let's look at an example of computing the center of mass of a solid. Let's take a tetrahedron shown in the first octant, bounded above by the plane x plus y plus z equals 1. And let's suppose that we have a density. Let's suppose that these guys are in feet, so that the density could be perhaps kilograms per cubic foot. And the output is just z. So if we want to compute mass, we want to integrate over the region of the solid, this three-dimensional region, and we want to add up a lot of pieces, a little piece of volume, dx, dy, dz, multiplied by the density. Think density, kilograms per cubic foot times cubic foot gives you kilograms, so a little piece of mass. So if we were to compute mass, we would have this integration right here. Notice how we set up the bounds. Let's just walk through it in this particular example. On the outside, we have dz. dz goes from 0 to 1. At a particular z value, we look at a cross section. You can take a look down here. Notice that this line on this side right here happens when y is 0, which makes this become x plus z equals 1. So solving for x right here in terms of z, it's 1 minus z. So x goes from 0 to 1 minus z, and right here, y would go from 0 to 1 minus z over here. Now let's pick y to go next. That means as y goes from 0 to 1 minus z, we pick a position at y and we look at that section. What is x doing? X is going from 0 right out to this, so from 0 right out to this plane right here, which is this. So we just solve for x in that plane. So we know x is traveling to there. Hence, we have this going from 0 to 1 minus y minus z. So then we go ahead and we integrate this whole thing one step at a time. Right here, we integrate first with respect to x. So the antiderivative would simply be zx. And then plugging in 0 is just 0. So we really just focus and concentrate on plugging this in. So it's just basically z times this, which is what we have right here. I just took z times that, and that's how I got this. Now from here, we want to be able to take an antiderivative with respect to y, and then plug in 1 minus z and 0. When we take an antiderivative with respect to y, we're going to have a zy minus zy squared over 2 minus a z squared y. And we're plugging in 1 minus z, plugging in 0. Again, plugging in 0 in this case, you can check, and you should check every time in case it doesn't. You will get 0. But when we plug in 1 minus z, let's see what happens. So the things that don't have y's, it's almost as if we're just taking it and multiplying it by 1 minus z. So notice I have z times 1 minus z. I just plop that down right there. And this one, minus z squared times 1 minus z, I just plopped it down right here. Now what about this guy? Well, intuitively in my mind, I thought, well, we are multiplying negative z times y squared over 2, or 1 minus z quantity squared over 2. So I knew that 1 minus z squared was 1 minus 2z plus z squared. And then, so that would be like a y squared. Then you multiply it by half. And then I know I'm taking all that and I'm multiplying it by this negative z right here. So in that process, that's how I got these middle terms right here. All right. Then from there, combine like terms to get this. Take an antiderivative. When we plug in 0, we'll just have 0. So we just basically plug in 1. Do a little arithmetic, we get 1 over 24. So the mass is 1 over 24. How do we find our x bar, y bar, and z bar? Well, x bar is going to be 1 over the mass. The mass is 1 over 24. So 1 over the mass is just 24 itself, multiplied by the integral over this region of x times our dm here, where this is our dm. It's like we have 1 over total mass or length of the mass interval, and then we're integrating the function x with respect to mass. So we're literally finding the average value of x with respect to mass. Okay, so in doing that, we just walk through the integration in a similar process of what we did over here. Here, with respect to y, basically I'm taking xz and multiplying it by that to get this first bit. Then here, use a similar technique for how I got this line to get, let's see, to get this line. However, we kind of just, maybe we didn't multiply it out completely like that. So in this particular case, let's see what we do. So we're integrating with respect to x. So we're going to have like a x squared over 2, x cubed over 3, x squared over 2. And then I basically just put in the 1 minus z's in here. Because we're going to do a little substitution since we have all the 1 minus z's showing up here. We plugged in 0. We're going to get 0. You can double check that for x in the antiderivative. So pretty much I take the antiderivative, but then I'm just plugging in 1 minus z into it. From here, a little substitution, I can swap places where I have a u squared times 1 minus u. And that's where I get this right here. This, similarly, I have kind of a similar type swap situation where I get u cubed times 1 minus u. That's how I get that. And then over here, we do in the swap's a little bit more complicated because we have u squared times, but then we have like quantity 1 minus u squared, but still looks better than when it would have otherwise. And so then we multiply the u squared into that. Well, it looks about the same, I guess. Yeah, it's about the same, but nonetheless, at least we can keep it uniform as u. So this one really didn't really help at all, but it's about the same as what it would have been. Okay, but we get this in this form, combine like terms to get this, and then we take antiderivatives and then plug in 1. So imagine this u cubed, you're going to get a 1/4 because u to the 4th over 4. That's where we get this 1 over 24. Similarly for here, we're going to get a 1/5 out of that. Okay, and in making this computation, we end up getting a 5th for x bar. Y bar should be the exact same. And think about why. Because the density function is z, depends on how dense you are going z, but x and y this way are symmetric. So we should imagine that x bar and y bar should be the same. Yet z bar should be different. And indeed it is in a calculation over here. The antiderivatives and process is nearly the same. Notice that we have our density times z. So take our density function, which is this, and then we're finding the average of z with respect to mass. So it's quite literally what we're doing is we're taking z times dm. Well, dm involves another z right here. So you have to think z times z is what we're looking at here when we calculate the z bar. Again, we have 1 over mass, which is just 24. We work through this and we end up getting 2/5. So we have been successful at computing the center of mass. The center of mass occurs at the point 1/5, 1/5, and 2/5. Thanks for watching.